Hello folks, welcome to part 4B of this sequence of this video, and we will continue demonstrating the development of this stepper motor drive. Works with all the features. I may run into some limitation, maybe programming a large scale application. When I get to that, I'll figure out. But right now, for smaller code, it's fine. All the features work. I'm happy with it. So I'll use this in our demonstration. And actually, I already had prepared a project, and I recorded probably 20 or so videos on this project, and then I found out that the audio or on my videos were all corrupted or somehow was interrupted by noise throughout in every single video. So I could open this. It's better. I think it's better if I start with a new one, and we can go through that demonstration. So what I want to do is create a new project. Oh, not a new file, a new project. So open the project wizard, go through those steps again, and before I do that, I don't like to use the standard location. It's just not in my desired folder location. So I like to keep my projects in a single location where everything is concentrated, any kind of project that I run. So let's see where I want to keep this one right now. Give me a moment, please. Yes, okay. So essentially I have a location. I've created some additional projects. Might as well let's see, but I'm thinking what name I can give you. Let's say it's number 2. Create a new folder with number 2, test 2, and yeah, choose. This is my number 2. Next, it's an empty project right now. And where is my D10-nano box? I have written down the exact chip. We'll get to that step. So next one, this is the step I wanted to prepare for myself. Okay, so my D10-nano Cyclone 5 chip is this 5CS EBA 6U 23I7. Now, in my case, it's I7N, but I don't have a N available in my data or in my list, and I have no idea how to add this one in there. So for now, since I don't need a large gate array to support my program, I want to use this, and this option is working. No issues with it. So I'll select this. Next, I don't want to simulate my code. Basically, once you build this option helps you just visualize at least, I believe, 100 nanoseconds or 10 milliseconds, something like that. It will give you the pulse output of the entire program. Well, not the entire program, the selective signals from the program, and you can figure out where the error is happening. So that's the simulation. I don't want to use that right now. Just want to continue, build a simple program. Finish. Okay, so do you want to continue? Yes, I want to continue. And like I said, I've already prepared one before, but for sake of this video, I want to go through it one more time. It's difficult for me to be surprised from different things. If I do get surprised, I will be surprised. But I have the program open on the other side, and this is what it was. Like I said, I had recorded all the 20 videos, and then found out the audio issue. So anyways, we'll continue with this. Okay, so once you create the project will be empty. There will be no files inside the project. Let's see what it looks like in our core disk. This is where it is. D10-nano test 2, and this is what you get. The QF, QSF, some files, simple configuration project files. Alright, so I want to add my VHDL file to it. And well, let's see, where is it at? My main program. I'll start with these libraries first. Oh, one other thing. Yes, let's do save as. And make sure that you save it with that exact name, so that the top entity will be this code, this VHDL file. And I know it says VHD, but it's actually VHDL file. So this is our top entity. Even if it's not, you could make it your top entity. Go to your files and you can say this is my top entity, and now it is. Okay, so these are all the libraries so far I've used. No explanation. I have no explanation for you at this point. These are standard libraries that you will use. Altera library, at some point I wanted to use some attributes from the Altera library. Maybe when I get to a point where I'm scaling this code up, then I'll use it. For now, I just want to copy paste from my original code, and I don't want to explain at this point what each library is about. That's what this video is not about, explaining each and every detail, and that will just slow us down. So I just want to demonstrate exactly how this is done and move on. If you have any questions, post it on my video, and I'll answer it with the best of my ability. So alright, so we'll start building our entity. So our entity is our project, the main project, which is FPGA. Let me see if it's still nope, not in there. Let me see if I can copy it from, yeah. So our project is FPGA CG4 test 2. That is our entity, and the entity is the entire project. Basically, it holds all the pins that the program will use. So I'm going to end the entity, and then we need a architecture of that entity. Let's say this is our demo. We can name it, this is basically the name of this architecture, demo, and it is part of our project, our entity. And let's see, at some point the architecture will begin, and it will, I believe it's end, or let me see, yes, it's end. Okay, now this is our skeleton, and in the entity we want to describe our ports. ports are basically our connection points that we will specify. Let's say for LED, we'll specify a switch. There will be, all these will be defined here in the port. And when we do a simple synthesis or analysis, that those ports will be available in pin planner, and then we could map those ports to the correct pin on our D10 Nano. Okay, so let's say we want well, first things first. For every FPGA, your SoC or FPGA, you need to know which clock you're going to use. In our case, we know we need a 50 megahertz clock, which is basically there's 3 different clock sources provided from the FPGA provided in the D10 Nano, and we have to make sure that we have that clock in place, because everything in the FPGA world is driven by a clock. You don't have a clock, then your program isn't going to function. So make sure that you have the clock defined. STD logic. Okay, so that's one thing. Next is LED pin. Now we know we want to connect to a LED. We want to show a simple pulse. Now LED is basically, as you see, let me turn on my camera and we'll see exactly what I mean by that. Okay, where is my camera? Ah, there you are. Okay, so LED is basically, you see this flashing light here. This is the LED I'm referring to in my code. I believe this is number 1. It's from right to left. So LED pin I want to use is, let's see, is going to be a in-out type. Now what does that mean? In-out, I'm defining in-out for LED. That means that I can read the LED pin state, which is the out feature or the out property, and in is the write property of the LED pin. It's a single bit STD logic. I'm just saying that this is the logic type, so it's basically this is a single bit, and basically we can read and write. We'll get to that point why later on in this code. Just hold on with me for a few minutes more. Okay, so next thing we need is a motor output pin. Now, why do we need a motor output? How are we going to use that? Well, we have a stepper motor. A stepper motor work on the basis of steps. So if you provide pulse to those steps, the motor will turn. So what we will do in our code is basically, however we flash our LED, we'll just forward that same logic or the same state of that pin to this motor output pin. So this is going to be our output. So this is our GPIO pin, and this is going to be out STD logic. And yeah, okay, so that's one LED and motor output. Now what we want to do, this is a very basic. We'll scale this up in the next attempt or in the next step. For now, let's build this. And well, I don't mean build, but let's just use this as our skeleton, and just build from this. So the next step I want to do is count our clock. So clock is giving us pulses at 50 megahertz. This is basically 50 megahertz clock pulse. And 50 megahertz is a very fast pulse rate. It will not be registered or registerable, or if we put this out straight to our LED, we will just see a solid LED on in the on state, and that's it. We will not see a change, and that will not do much. We want to flash it basically just like that, like this is flashing. So what we want to do is basically slow down that clock, and for that we have to do a build a clock divider. So clock divider will help basically help us slow down this output just enough so we can see it. And in the clock divider, we'll just take this clock as is. We have to specify which is our trigger. So basically this clock is our trigger for this process, and we want to see if the pulse is going high on the clock. We want to do something. Okay, so what do we want to do? We want to count. We want to count this pulse. The more we count, basically we're going to the further we're going to divide the pulse. We'll take that count and we'll say, okay, if we reach that count, let's say we're counting to 15. Every time we receive a pulse, it's going to count 1, 1, 1, 1, 1, and when it reaches 15, then we'll say, okay, give me another pulse output from this process, and then we'll take that output and push that into another process, and that process will, inside that process, we will then change the state of our LED, and the state, same with the motor output pin as well. So let's do that. Clock count. Oops, clock count will be incremented. I didn't build this clock count yet. Clock count is a signal. Let me complete this process first so we can see what is going on, and the end process. Alright, clock count. This we have to declare in here. Let me see exactly how I declared this, so I'm not making any mistake. Yes, simple signal clock count, and we're going to declare a 24-bit clock count. 24-bit basically will allow us, let's see what it's going to allow us to do. 24-bit clock count Excel. It will basically count to 16 million 777,215. So it's a very large number. However, we are not going to use all 24 bits. It's basically just a way for me to keep a consistency in this code and my other code. We could go lower. We could count, let's say, 15 bits or 20 bits. We can do that as well. So just to keep it consistent with my demo code, I want to keep it at 24 bits. Okay, so I have 24 bits and we are counting, and as we count, the number is going to be stored locally in this architecture. And we also want to do something else. We want to pulse out at certain point when the pulse or the count reaches at a certain point. So that what we want to do is say clock count, give me a pulse at about 15, basically reading bit 15. Every time bit 15 goes high, we will forward that pulse. And this is our, I think this is 12 kilohertz. Let's see, how can I explain this? Yeah, the best explanation, built a little table for us. So essentially bit 15 is somewhere here. This is not a 12 kilohertz or 12 yeah, this is not a 12 kilohertz. 12 kilohertz is somewhere here at bit 11. 15 is actually 762 hertz. It's even slower. Let's leave it at 12 at this point. Like I said, I want to keep it consistent. But essentially, that's what's going on. If you let me explain a little bit here, if I may. Let me explain a little bit here. So essentially, what's going on? These are the bits or the bit counts in the 24-bit position. So 0 through 24. At first one, we will get a half frequency. So if we are not counting at all, we get the same 50 megahertz output. If we are counting the first bit, if we say, okay, give me the first bit, that means that we are counting half of the pulse. We are dividing that pulse into two pulses. Then if we go further, it will be at 12, half of the 25, and then half, and then half, and then half. Basically dividing by 2 every time we look at different bit position in that byte. So okay, that is basically what we're doing. Hope that helps. So we're going to watch the bit 15, which will give us 762 hertz. We will take that. Let me just change that. 762 hertz. All right. I don't think there's any issue with the name. If there is, it will tell us. All right. So this is just STD logic, and STD logic we will use. So just like this process, we take this and build another process, which is our LED out. And LED out will use that pulse output. The 762 hertz, it will take that, and we will look at the rising edge of that pulse. And as we do that, we will also say, okay, at that rising edge, give me a simple output, and I'll take that output and send that to our LED. Let's remove this. Our LED is pinned right here, and we will change the state of our LED. Whatever the state is, 0 or 1, it's going to be opposite of that. And then we will do a write to our motor pin as well. Take the same LED pin, write it to the motor pin. Okay, very simple code. Let's see what we can do here. Let me see. Save, and I'm going to do a compile. Let's see if it do a quick compile. And as it's compiling, if there's no error, let me remove. Oh, I apologize. My screen was on. Let me remove this view. Okay, so it's compiling. Essentially, what I wrote down was this: LED out process. So something is bothering it. We'll get to that. I think it'll stop. Oh, it stopped already. Okay, that's fine. Port, yes. I think that last one shouldn't be terminated. And yeah, I'm using the right notation. Semicolon is right. And what is the other one? Begin. Begin don't need. Let me see if there's a missing notation here as well. I don't think so. I think this should be fine with, maybe it just propagated from the top level. Let's see if it happens now. Okay, I think it's moving. I think it's moving. Yes, it's moving. Okay, 26%. This is good. This is a very simple code. Very simple code. We declared a few pins. We have two different types of signals. Well, not types, I would say. Similar types, but one is array, the other is a single bit. And then we have two processes. One is simply counting the clock pulses. The other one takes in the output of that clock pulse and then just change the state of the LED and motor pins. All right, let's come back to this. I think it's going to take a little bit more time. Okay, folks, now the compilation is done. No errors. And what we will do, we will look at our pin planner. Maybe I should have just done a simple synthesis. That would have given me the pins, and then I could map them easily. Okay. Yeah, I could have saved a little bit more time there. What I want to do now is find out exactly which one of the pins I need to use. Alright, I have the manual open, and what I want to use is, there is a table. Yeah, there's this table. I want to know my GPIO0. Let's look at this first. So GPIO0 is the one to the right of, so using our Ethernet connection as our reference, right side has the GPIO0, left side has the GPIO1, and what I want to do, or you can say, okay, the one next to the power connection, and what I want to do is use the GPIO0, and it starts from, as you can see, the pin that is closest to the power connector. Pin 1 is that, and then obviously pin 2, and then 3, 4, 5, 6. That's how it goes. And here you can see the odd pins are on one side, even pins are on the other side. And what I want to do is basically pick out pin 10 and pin 12 because it's easier for me to connect the ground. I don't want to have ground here and pin 1 here, then the two pins I have to connect to is just too far and messy connection. I don't like that. Pin 10 and pin 12 is what I'm going to choose. Pin 10 will be our motor output pin, and the ground will be the ground. And okay, so that's our motor pin. So let's do that. Location, and this is what you do is basically just write this notation AH3. This is the ID of that pin. And let's see, we want to know our clock. I think I jumped the gun there. I should have looked for the clock first and then anything else. So the clock is, let's see, where are you? Yeah, there you go. There are 350 megahertz clocks. I will take the first one, V11. And what I want to do is look for my LED pinouts. LED pinouts. That's not the one. It's somewhere up here. Okay, let's see. Yeah, there you go. You see this LED array? I'll take the very first one. If I take the other one on the other side, let's see. I don't know if it's, yeah, it's, I can do that. I can take the LED 5 as well. So you can see this is the default code right now. If we download, it'll make a different pulse on the other one. So something different. AE26 is our pin. Okay. Pins are defined. And we close. Let's keep it up here. Okay. 3 pins, they're all defined. I save it and then I run it again. We'll come back when it's ready. Alright folks, so it's done 100%. So once this is complete, there is a file the project creates. Let me see, this is our folder and this is our VHT file, other project files. So look for output files and you want to look for this SOF. This is the binary this project creates, or the Quartus creates, and this is the one we will use to flash our FPGA with. So how we can flash? Now, right now we have our UART connection. What I'm going to do, I'm going to unplug this UART connection and connect. Let me see if I can turn on the video so it's easier for me to explain. So folks, it didn't write correctly. I'm using a incorrect configuration. So this is one of the things that you have to remember on this D10 Nano. It comes with a select switch configuration. Let me turn on the camera. Let's see if the camera is still on. Yeah, okay, it's working. So this switch right here is currently configured for HPS programming. Yeah, right there. And what I need to do is change it to FPGA programming mode. So to do that, I have to look at my MCell select switch and set it to program as it is programming from the EPCS. So let's turn it off first before I do that. And it's basically on, off, on, off. This last switch, second last switch has to be down. These two have to be up, up, and this one has to be down. Okay, let's plug it back in. And I'm going to reprogram this. Okay, let's see if this works now. Ah, no connection. Hold on. Hardware is back. Okay. This is the one we want to. I want to make sure that a fresh file is loaded. Okay. This is the one we're going to program, and we will program. Alright, something is programmed successfully. Let's make sure it's functioning. And it is not functioning. Something isn't right. Are we programming pin 10? Did we program it right? Let's go back our pin planner. Our LED pin AE26. And I believe it's down here somewhere. Yeah. AE26. And this is bank 5A. I don't really care about the bank and all that, but this is bidirectional. The motor pin should be GPIO 010 AH3 in my case. I don't know if it's the same one. GPIO 0 pin 10 is AH3. That is correct. Let me make sure my other pin. No, I don't have the configuration right now, but maybe it is forwarding to a different pin. AH3 is GPIO 0. There's a GPIO 1 on this side, but I'm sure I'm not using that one. AH3, 3B is my pin, but it is not working. I can do a test. Instead of uploading this one, I can upload another one that I have programmed earlier. Make sure this pin is okay. Yeah, the light is flickering. That's good. My motor isn't turning. Ah, wrong pin. Apologies, everybody. So, okay, let's go back to our. This is why I need two different programs to make sure that I'm not making mistakes. So this is as I said, I had recorded like 20 videos, and they were all corrupted by, maybe it was this noise amplified into the audio. But anyways, it is working very well. Let me smooth it down a little bit. Yeah, this is good. So let's upload our program. We will go back, and I can make this video a bit smaller so you can see what's going on. Okay, where is this? Is our number 2 that we created, output files, and yes, this is the one, and we will upload this code, and there it goes. Okay, so 762 Hertz. This is the speed, and it's not changeable at this time, but we can make it changeable. That we will do in the next step. So for now, I'll stop it here, and then I'll proceed when I'm ready. Okay folks, so in the next step we are going to count using the switch configuration. So let me turn my camera on, and let me show you what I mean by that, by the switch configuration. So okay, video is working, that's good. So what I mean by the switch configuration is these 4 switches. What I'm going to do is map the I/O or the switch I/O into our program, and we're going to use these 4 switches as 4 bits, and then we're going to use this as a counter from 0 to 15. So when we're at 0, it will execute with the maximum frequency that it can achieve, 12 kilohertz, and with that frequency then we can slow down further, 1, 2, 3, 4, 5, 6, 7 to all the way to 15. So basically that's what we're going to do, and let's begin. Let's see if we can. I'm going to turn this video off so it doesn't hide the document behind us. I get more screen, so I can get more screen space, and let me do that. Yes. So what I want to do, no, I cannot squeeze this any further. So okay, let's continue with this, and I'm going to say, let's say what I want to do is I want to have another process where I count the switch. So I'll say switch count process. I'll take the 762 Hertz, and then process, begin and end process. All right, so 762 Hertz. Let's say we are going to, let's say we are going to have a switch, we're going to have a switch count. Actually, switch, let's say bit count. All right, so these are the bits representing the switch, and or the series of switches that we have. And what we want to do is we want to do a counter. Let's see, do we have the same name anywhere here as a counter? I'll say set switch counter, SW counter. And if this reaches, if the switch bit is equal to switch counter, I want to do something. What I want to do is I want to send a pulse out. Basically, let's say SW pulse out, and which is going to be basically a notch of SW pulse out. Alright, when it's equal, yeah, it's going to just do that, and we are also going to zero out the counter. I'm hitting too many keys together. Let me do it slowly. I'm trying to go too fast. Let's slow down. Slowing down is good. Okay, so when it's equal to the counter, we're going to send the pulse out, and we are going to reset the counter. If not, we're just going to increase the counter. Basically, that's as simple as it is. Basically, it is this simple. So essentially, every time this pulse comes in, we can slow this down even further. I think 15 was, yeah, it's 762. So 762 hertz pulse comes in, we match it against our process counter, and if it's equal, we reset our process counter and send out a second pulse, and this pulse is basically will be used by our LED and our motor. So basically what we will do is we will push this pulse, which is variable, which is going to be a variable pulse. So that will go into this process, and it will reset the state of LED, and then the same for the motor pin. Okay, so here we are. Pulse out. Goes here. And let's put this in the right sequence. Everything else stays the same, and we have to make sure that we create these new pins for our program. So this is in std logic. Let's turn this into an array. I wish there was a nice shortcut method in the Quartus, but it just doesn't give us that option. Maybe in the Pro version it does. So it is going to be 3 down to 0. This is our 4 bits. So switch bit comes in, connected here, and we also need the counter. Counter will be 4-bit as well. Similar to this, we'll do it. Oh, signal count. Just making a copy. And this will be a 3 down to 0. Okay, so switch counter, and we need a pulse as well. Pulse out. Yeah, this is going to be a local, just like our 762 hertz. This is going to be another signal. Oh, what is going on? Interesting. I didn't copy paste that many times. What's going on? Let's do it again. Pulse out. Interesting. Okay. So our switch count will be compared against our process count. If it's equal, we're going to pulse the switch, pulse out, and reset our counter. Otherwise, we'll keep on counting. And then this comes down here. Okay. Let's see what this does. Let's compile. Oh, before we compile, I think let's check if the program pin map detects a change. It hasn't. So I have to do a synthesis, and this, I believe this helps the program detect a change in the pin map. So let's see what happens here. Okay, few mistakes. Let's correct those. Where are they? Oh, process. There's no is statement, just to begin, and it is expecting a terminator. It's not sure exactly where. Okay, let's do our homework first here. 1, 2, 3. No need here. Those are the new additions. They're fine. This should be okay. I believe that was the only. Oh, okay. I see. Yes, yes. There's one right there. Okay, let's do this again. Synthesis. Oh, it doesn't want to use 0. I think it's 000. My reset count. Okay. Found one of the mistakes. I have a mistake here. I should have 0 this one as well. Not sure, it doesn't like the std vector type, does not match the literal. I think this requires a full bit representation, so actually it's going to be all zeros. How can I do all zeros? Let's see. This is and here switch counter is a 4-bit counter, so 1, 2, 3, 4. This is a 24-bit counter, so this should be, let's see if it does give us 15, 20, 1, 2, 3, 4, 24 bits. Okay, there you go. That should be suffice. That should suffice. Let's see. There's another method to overwrite all bits, and there's a notation to override all bits, and I can use that to override all all 24 bits to 0. I could do that. Okay, for now this is fine. Let's make sure our switch pins are mapped. We have 4 bits here. Let me make sure I'm not recording my video over, and let's see our pin map. Ah, there you go. Okay, so the document, and it doesn't like to be open. both at the same time. Let me see if I can make this any smaller. Okay, now it's gonna be fine. Alright, so I think this page has our switch pins. Yeah, there they are. 0 is Y24 and 1 is W24, 2 is W21, and 3 is W20. There we go. Closing. And now we will do a full compile. This will create the SOI file, and then we can download that to our card. Let's. I'm going to hit pause, and I'll come back once this compilation is done. Okay, folks. So finally, it finished the compilation, and we can download this to our board. Let's see. Let me turn on the video. And let's see. I have the power unplugged right now to the motor, so that's why it's not moving. It's still running the same code, same old code without the switch. So I am going to open our programmer, reload our SOF file. Let's see, yeah, there you go. Output files. It's slower. Okay, so file is loaded. This is the one we are going to program, and program is done. The light is off. Let's see what's going on. This is different. Maybe my pin connection isn't right. Let me see. Oh, okay. I am resetting. I believe my reset is causing the clock to go back to a very... Folks, I'm stopping the video here, and we will continue this demonstration in part 4C. So see you in that video, and stay curious.